So this section is called the limits of radial motion and effective potential. And we're going to basically continue with the conservation of energy equation. So we had 1/2 mv squared plus the kinetic energy as a function of r is some constant total energy. And we're going to be able to tell from this equation, when we break it down a little further, what the limits of r are for the object. These two have to be equal. And so it puts constraints on how far away the particle can get, because its potential energy gets greater as it gets farther away, and the sum of these two can't exceed the total energy. And so we'll learn a few things from that. If you remember, the velocity, we turn this into a differential equation by first breaking down the velocities and saying v squared is equal to v dot v, and that was equal to r dot dotted into r dot, right, where r dot is d by dt on r e hat r, and that gave r dot e hat r minus r theta dot e hat theta. And then we had to dot that back into itself and got a couple of terms in there, and we ended up with an equation that looked like this. It was and then we recognized from earlier in the chapter that theta dot was equal to L over R squared. There we go. And so theta dot squared is L squared over R to the fourth. And so this could be replaced with m over 2 r dot squared plus r squared times L squared over R to the fourth plus v of r is equal to E. Some of those guys cancel, and we get m over 2 r dot squared plus L squared over R squared plus v of r is equal to E. If I expand this out, I get a half m r dot squared. Notice that's the radial velocity, right? So it's you might say it's the radial part of the kinetic energy, plus m L squared, squared over 2r squared plus v of r is equal to E. And so you can kind of call this piece the radial kinetic energy. And what we often do is combine this piece and this piece and call this the effective potential. The effective potential energy. And so the radiokinetic energy plus the effective kinetic energy is equal to the total energy. And so we can do some graphs of this and look at this function a little bit. So again, this is our equation. It's the energy equation. R dot is the radial velocity. U is the effective potential we talked about last time. It's defined down here. And we can say, look, when R dot is 0, that means this effective potential here has to equal the total energy, right? And so if you're looking at an object that it's in its orbit, it's got a minimum value of r and a maximum value of r. It's the perigee and apogee if it's orbiting the Earth. And those are where its radial velocities are 0. It's come all the way in radially at the perigee, it's gone all the way out at the apogee. And that means these two terms have to be equal to each other. And so if we just pick a general form of the equation, and we say, look, the potential energy is just minus k over r, where k is just some constant. We can pick, choose k and L equal to 1, just to make this simple. Maybe we'll also pick m equal 1. Right. And so this says, at the top we have u of r is equal to e, because we're at perigee or apogee, and so r dot is 0. And this means that that 1 over 2r squared minus 1 over r is equal to e, right? And so we can solve this equation for r. So this is our energy equation. That's the radial velocity. This is a sort of the radial kinetic energy, you might say. This is the thing we call the effective potential. It includes this piece of the kinetic energy term and this piece of the potential energy. This is what we did on the last screen, right? And so what we're saying is, look, if you have some case like a satellite orbiting something, it could be a star or something like that, right? Then when the satellite gets to this point, the perigee, if it's orbiting the Earth, right, then r dot has to be 0. Its radial velocity isn't increasing or decreasing at the minimum or at the maximum. And so at these 2 points, this term goes away, and so we could say at the extrema, u of r is equal to e. We can use our knowledge of those things, those functions, to figure out what the values of r are at the limits, right? And so we can say, look, if we're going to have a 1 over r squared for us, we can say v of r is equal to minus k over r. Right, that's the potential energy. If this is a gravitational potential, it's a GMM, but it could be anything, right? We're choosing it as 1 over r squared force, so a 1 over r potential. And so we can say, look, u of r is equal to e, and that means ml squared over 2r squared minus k over r is equal to e. And just to make things simple so that we can look at some stuff on some graphs, we're going to pick m equals l equals k equals 1. I just want to simplify everything but e and r, right? And this gives me 1 over 2r squared minus 1 over r equals e. And I'm going to insert some graphs in here. But first I can just multiply through by r squared, and I get a 1 minus 2r squared over r equals 2r squared e. Right, this becomes a 2r. And so what I get is 2e r squared plus 2r minus 1 equals 0. That's a quadratic equation in r. And generally speaking, it has 2 roots, right? And so I can evaluate them using the quadratic formula. I can say, r equals negative b, which is negative 2, plus or minus the square root of b squared, which is 4, minus 4 times, a, which is 2e, that's the coefficient of the r squared terms, times c, which is minus 1, all over 2a, which is 2 times 2e. Right? If I simplify that, am I still on the screen here? If I simplify that, I get r equals negative 2 plus or minus, so this becomes 4 plus 8e, so the square root of 4 plus 8e all over 4e. And so that can make that a, so if I divide it, so I'm going to pull a 4 out of the radical, and that'll put a 2 in front of it. And this will be a minus 1 plus or minus the square root of 1 plus 2e over 2e. And you can check my math on that. And so these are the limits on r, right? And so I'll just evaluate a couple of those and put up a graph of them on the next screen. Okay. So we can evaluate some of these. So the limits on r is r equals negative 1 plus or minus the square root of 1 plus 2e over all over 2e, right? Here we picked, m equals L equals K equals 1. We could pick a little more realistic example than that, but we've just chosen those things to make it simple to graph, right? And so you'll see the graph coming up here in a second, but if I pick e equals minus 0.4, I get r equals this, and this is negative 1. Sorry, it's a negative 0.8, right? It's minus 2e. Plus or minus the square root of 0.2 all over minus 0.8, and that gives me r is equal to, so that's a 1.25, and if I want to I can say minus plus 0.45. Comes out to about 0.56, and so r goes from 0.7 to about 1.8. That's the range. So that's the minimum r and that's the maximum r, right? And you'll see it on the graph on the next one. I have some horizontal lines for the graph. So let's pick a different one. So equals minus 0.2. When you look at the graph, you'll see why I picked these. That's equal to minus 1 plus or minus the square root of, so it's 1 plus 2 times e, so it's negative 0.2 over 2e, which is minus 0.4, and so that's 2.5 plus or minus, and so this is the square root of 0.6, right, which is about 0.75. So this is r equals, or r equals a 2.5 plus or minus 1.93, and so that's about 4.4 and 0.6 for the minimum. Right. And so once again, you'll see that on the graph next time. Suppose we pick something like equals 1 here, and now we get r equals negative 1 plus or minus the square root of 1 plus 2 over 2. Right. That's equal to negative 1 1/2 plus or minus the square root of 3 over 2. Right, and that gives us this gives us r equals 0.36 and minus 1.36. The problem is r can't be negative. R is the radial distance, and so it's not a negative number, and so there's no negative value for r. And so this one goes away, and you'll see there's only one value of r and its minimum r. And what this means is that the orbit is either hyperbolic or parabolic, and there's no maximum distance, there's just a minimum distance. So these are the three graphs of the blue curve here is the potential energy. It's minus k over r. That's the blue curve. The red curve is the ml squared over 2r squared. It's the, you might say, it's the angular part of the kinetic energy term. And then the u of r is the effective potential. It's the sum of those two. And it's this green curve. And what we calculated is the radial extents of the trajectory based on different energies. And the first one we did was, I think, minus 0.4, and that corresponds to this black line. This black line, if you can look over here at the y-axis, is at minus 0.4, and that's the energy. And that's where the radial extent is the limits of where the energy curve crosses the effective potential. If this is the effective potential energy, the energy of the particle has to be above that to appear in the to get there. And so you can't have a total energy that's below your potential energy and have your particle be there. And so the range of the particle's motion in r goes from this point, which is at about 1.8, to this point, which is about 1.7, and those were the two numbers we calculated for an energy equals minus 0.4. This is an ellipse with an apogee of 1.8 and a perigee of minus 1.7, or a pericenter and an apocenter. Then we did it again at 0.2, and we got about 0.5 and something like, or 0.6, and 4.4 or something like that. And those are the two places where the black curve crosses the effective potential green curve for energy of minus 0.2. And then we went all the way up here to an energy of 1. And that corresponds to about 0.3 something, which was what we got. And notice there's no second place for the curve to cross. Our second answer was negative. And the r is just the magnitude of the distance of the particle from the origin, so there's no negative value of r. And what this means is that the particle has enough energy to escape and isn't trapped, so it doesn't have a maximum r, it just has a minimum r, and that's what we got as 0.36 on that curve. We can come back to this maybe later and adjust some of these r and k. Remember, it was negative k over r was the potential energy, and ml squared over 2r squared was the maybe the angular momentum part of the kinetic energy that fits into the effective potential. And so you can and we could model some different problems that way. But these where the black lines cross the green curve is where the effective potential would be, where the limits would be in R. So in the general case, we can determine the limits on R in an orbit, once again, by just saying the radiokinetic energy equal to 0, and the effective potential minus the energy is then equal to 0. And so we can write this way. And then if V of R is minus k over r, right, then we get ml squared over 2r squared minus k over r minus e equals 0. I can multiply through by 2r squared, and I get ml squared minus 2kr minus 2er squared is equal to 0, or 2er squared plus 2kr minus ml squared is equal to 0. Once again, a quadratic, just like I had a few minutes ago. And then I can just solve for r using the quadratic formula again. I get r is equal to negative b, which is minus 2k, plus or minus the square root of b squared, which is 4k squared, minus 4 times a, which is 2e, times c, which is minus ml squared, all over 2a, which is 4 times e. Right. And so I can factor 4 out of the top one and put a 2 out here, and so I get a minus k plus or minus square root of and so this is k squared plus, I lose the 4, and it's 2 ml squared e, 2 ml squared e, all over 2e. And those are the extrema in R, right? Hopefully that's all on there.